Hello, everybody, and welcome back. Our next speaker needs absolutely no introduction. So please join me in welcoming to the Hackaday Supercon stage, Jeroen Domburg, aka Sprite TM.
Thanks so much. Just adjust the mic a bit. Okay, so my talk is going to be building a portable Vectrex the right way. And one question you might have is, what the hell is a Vectrex? So this is a Vectrex. This is an idealized picture. The Vectrex was a game console that they designed in 1982. Just as an indication, these were the most common consoles around the time, the Atari 2600 and the Intellivision, very big pixels. So to give you a better introduction on what the Vectrex is, I'm going to show you an advertisement they run at that time, so please disable your ad blockers.
This is the system chosen 2-to-1 over Atari and Intellivision for real arcade gameplay.
Fantastic!
Presenting the revolutionary Vectrex arcade system. Ordinary home video games can't match the laser-sharp visual effects of Vectrex, because only Vectrex has a real arcade screen built in. No TV set needed, so every Vectrex cartridge gives you real arcade gameplay that others can't. Vectrex, it stands alone.
Yeah, it was acceptable in the 80s. Okay, so obviously we like games, but as Hackaday people, we like more what's inside the games. And so I'd like to go over what's inside the Vectrex a little bit. And that's very easy because there is a full service manual out there. And not only that, but also the Vectrex uses all off-the-shelf chips. There's no custom ASIC in there, nothing that needs to be reverse engineered. You can just get the data sheets for everything. Up to a point where Eric, TubeTime, actually made a replica mainboard of the Vectrex that you can connect to your scope in XY mode. And if you want to, you can just play Vectrex games on your oscilloscope. So let's just go over the digital bits of the schematic. So we have the cartridge here. The Vectrex is a cartridge-based system. The cartridges just contain a little ROM and that's it. No DRM or whatever. Main CPU is a 6809, which is an 8-bit CPU that came a little bit later than the 6502 you may all know and love. It's a fairly fast processor. It's got an 8-bit multiplier integrated. There's 8 kilobytes of ROM that is split into two parts. 4 kilobytes contain what's called the executive, which is sort of the BIOS. It has a bunch of utility routines and the startup code, etc. And the other half is contains Minesweeper, which is a built-in game. We also have the RAM, that's 1 kilobyte if I recall correctly, which is like 8 times as much as the Atari 2600. A little bit more to the right we have the PIO, or VIA, depending on who you ask, which is effectively a way to add GPIO to the 6809. It also contains 2 timers and a shift register. We have the audio, which is an AI3 8912, which is a 3-channel thing that can do bleepies and bloopies and noise generation, etc. And then here we have the GPU, which is an MC1408P, which, wait, that's not a GPU, that's a DA converter. So what the hell's going on here? Well, there's a whole bunch of logic that follows this DA converter. You have a multiplexer, you have multiple op-amps that act as integrators, you've got a bunch of switches. And then if you continue looking, it all goes through an amplifier into the deflection coils of the little CRT that's in there. What's going on with that? Well, first of all, I need to explain what deflection coils are. So if you have a classic CRT television, like, I don't know, you've maybe seen, in the garbage at the street stands, what they do is they steer the electron beam in what's called a raster scan. So it starts on the top left and then scans to the right, pooping out all the pixels. Then it draws a second line, pooping out more pixels, etc., etc., etc. And it does that over and over and over again. But because the deflection coils are under control of software, what the Vectrex can do is just steer it any way it wants to. And if it controls the intensity correctly, it can draw lines that way. So you can get like little images. And because this all is done in the analog domain, the lines are really crisp. There's no resolution there. They're like really sharp, even if they're diagonal. Okay, so with that being said, we now know what's in there. How do we smallify the Vectrex? Well, it's very obvious. You just do what everyone does. You take a Raspberry Pi, you put an LCD on there, you whip a controller up, you 3D print an exclosure, and you're done, right? 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 You just come on stage and you hold your talk. No, obviously you read the entire title, and we're going to do this the right way. And this comes with a caveat that when I say the right way, like 80% of you is probably going to disagree with me on some point or another. So I'm just going to say that this is what I think the right way is, and what I think the right way is might have been influenced along the way with things that are hard or impossible or whatever. So my main point with this is that as soon as you take a Vectrex and you put this output on an LCD, this is what you get. You don't get a line, you get pixels. And that's the one thing that the Vectrex doesn't have. So I have an opinion on this, and that is that you need to be able to draw lines, and a CRT would be the most like proper way to do that. Okay, so we're going to build this thing the right way. What do we need? Well, first of all, we need, this is a display of that. First of all, we need a CRT, obviously. We need to replicate the main logic somehow, so the 6809, etc. We need a way to drive that CRT, very importantly, and we need an enclosure. So let's start with the CRT. And if you look for something like a portable CRT or whatever, what you get is these 5-inch little CRTs that you can use in campers, etc. They do exist. And making a Vectrex out of them is actually not a weird idea, because at the end of its life, the people who designed the Vectrex actually came up with a mini Vectrex that's now a museum piece, because there's only like 1 or 2 in existence that use this. But this is not a portable Vectrex in the way I want to. Like, I want to, sit on the bus and then whip it out and play it. And this thing needs power, and it's not that easy. So we need another way. So, like, in the 90s and the 2000s, this is a thing that was on the market, which is a Sony Watchman, which is a little tiny television, well, relatively small, that has a CRT that has the electron gun at the bottom. So that way it can be very small. And this would be great were it not that, at least in my neck of the wood, these things aren't that easy to get, and it kind of feels dirty to destroy one of those things for that. I don't know. A device I don't really have that much of a problem with destroying are these things. These are video intercoms. So if you lived in an old flat, you may have seen them. There's a little camera down below, and if someone rings your doorbell, you get a little black and white image of their faces. These things are everywhere. You can get these on like anything for dollars. And the nice thing is that they all work around like similar modules. These are modules that are pretty similar size. They all take 12 volt. They all take composite, these are pretty universal. And if you look at the module, you'll kind of see that it resembles a game console, like an old school Game Boy, right? It's a bit more chunky, and I am not the first person to have figured that out. Bitlooney, who's here in the audience, actually took an ESP32, put a Game Boy emulator in that, and made the chunkiest Game Boy possible. So really nice. Okay, so we have the CRT. Now we need the control logic, the 6809, etc. And I could go the easy way and just chunk a microcontroller in there, but it feels more proper to do it using an FPGA. Again, it would be even more proper to do it using like the actual chips, like the scope. ScopeTrax did. But I kind of have an envelope to take care of, and I need to put more in there than just the Vectrex. So an FPGA it'll be. So I need to put a bunch of things in that FPGA in order to make it work, namely all the components that the Vectrex used. So the CPU, the VIA, the sound chip, and the analog simulator. So where do I get that? Well, you guys download the hardware of the internet, right? Download more RAM? So I got the 6809 from the Mister project. They had a real nice version that they improved from someone else's project. The VIC-20 had a 6255, like the VIA. There's a model for that, so I could just, copy the source code for that. And the ZX Spectrum Plus 128K has a sound chip that is actually a Yamaha, which is a slightly different chip, but it's backwards compatible with the chip in the Vectrex. So I could just use that, put it in the compatibility mode, and it works. And the analog simulator, well, if you look through all the analog magic, it's actually not that hard. These 4 lines are effectively the core of it. So, you know, so you take all that and you dump that into an FPGA. Obviously, the question is which FPGA is that? Well, this is a ColorLight CLI5, which is a little module that is supposed to go on the back of these big-ass LED screens. So it contains an ECP5, which is the FPGA. It has 25K LUTs. If you recall the 2019 batch, that had about twice. But it's still pretty big. It has 8 megabytes of SD-RAM, which is very useful. It has 2 megabytes of flash, of which about 512K is filled with the FPGA image. The rest is free to use. And it's got 2 gigabit PHYs, which I won't use. So module is pretty cheap. This is 27 bucks. I actually think I saw it somewhere for 12 bucks or something. And they're also very good for children's learning to read. Well, whatever. So we have a module. We still need to control the CRT somehow. And that is an entirely different chapter because CRTs are not easy. They work with like strange things like physics and stuff. Okay, this is one of those CRTs, and like on a high level, it's very simple. You just put a bunch of volts in here, you put a bunch more volts in here, and you get a little dot, and then you can move that dot around by putting a bunch of amps in here. That's it, easy, right? Well, oh yeah, if you move that around, you can draw images, obviously. It's a little bit more complicated. This is the side of a CRT, and it contains a bunch of electrodes, and you need to feed those electrodes the proper voltages, otherwise it won't work. So first of all, it has a heater, and in this particular case, the heater takes 10 volts. If you ever see a CRT like this, please don't assume that the heater takes 10 volts, because there's 2 types, one that takes 10 volts and the other one takes 0.6 volts. And you can probably imagine what happens if you put 10 volts on there. So then you've got four electrodes. The first one is called G1, and it controls the intensity of your little dot. So if you put 70 volt on there, give or take, then it's off. If you put 40 volt on there, it's on, entirely bright. You've got your G2, which is some sort of contrast setting. I don't know exactly how it works. And you've got your G3, which sets your focus. So you need to put the proper voltage on there to focus your little dot into an actual dot and not a circle. And finally, there is the anode, and that is a little bit scary because you need to put 5 kilovolts on there. Yay! Physics, great. Can't they just make physics 3.3 volt compatible? Anyway. So, how do you get all these voltages? Well, there's this nice little box on the original PCB that's called a flyback transformer. And the nice thing is that the scary 5-volt lead is just attached and nicely, put away with a silicone cup. So, hopefully you don't touch that. And the way you drive this thing is very easy. It's like you just look at the schematic and it's entirely clear, right? So at least the power supply bit was somewhat easy to reverse engineer. And this is the way I implemented it. So you've got your flyback transformer here. You've got a capacitor and an inductor to kind of decouple it. And then you've got a MOSFET that just pulls power through it like at a rate of 15 kilohertz. So on the other side, your flyback transformer just poops out the correct voltages. All you need to do is rectify that. Just a single diode would work. And you've got 40 volts, you've got 80 volts, you've got 400 volts, and with the diode that's integrated into the thing, you've got your 5 kilovolt, give or take. So that's easy. From that, you need to derive all the other voltages. So your G1, your G2, and your G3. G2 and G3 are very easy because those are fixed voltages. You just want to have a potentiometer to tweak them a little bit. So you just have to take the 400 volts and then put it to a resistive divider with a potentiometer somehow, and you've got your G2, and the same thing for your G3, just with different resistor values because G3 needs to be higher. And then you've got G1, and that is your intensity, and that needs to be controlled from the FPGA. And don't look too hard at this schematic because it's crap. I will. I'm really not happy with it, but it's good enough. Let's put it like that. So what it consists of is the FPGA has 7 bits in parallel that get output to a resistive DAC that converts it into a voltage from 0 to 3.3 volt. That then uses this schematic to give it a little bias, and finally there's this little bit that amplifies it to the 70 to 40 volt that we need. So if you have all this, you get this spectacular result. Okay. Thank you very much. But obviously we want to draw stuff with that. And for that we need to use the deflection coils. By the way, if you have a CRT like this, don't take the plastic off the deflection coils. This CRT unfortunately never has been the same. And for that we need to learn a little bit about coils. And I will try to make this as simple as possible, no math. So I'm just going to say that a coil is very similar to a pig. And you can actually see that because, you know, the symbol for a coil and the tail of a pig are kind of similar. So, you know, match made in heaven. So why is it similar to a pig? Well, the stereotypical pig is very stubborn. So if you were to push it, like it wouldn't immediately move. You need to push it a fair bit to get it to move. So if you linearize that, you know, spherical cows and stuff, you could say that the longer you push on the pig, the higher its velocity. So the faster it'll go. And obviously, it also works in the same way. If you've got a pig running towards you, you can't just immediately stop it. You need to apply power for a little bit in order to make it stop. So, you know, that kind of works in the same way. For an inductor, this is kind of similar. You can push an inductor by putting a voltage over it, for instance, from a battery. And rather than immediately having a certain set current, like you would with a resistor, the current will slowly increase. And if you take an ideal inductor, actually, and this feels a bit weird because we're not used to ideal inductors, if you then short circuit it, the current will just keep on running, strangely. And obviously, if you want to stop the current from running, you can take the same battery, but just, you know, put it in the other way around, and that will slowly decrease the current. And if you keep it like that long enough, it'll even go negative. Okay, so that was my TED talk. A coil is like a pig. So. Okay, so why is this important? Well, the deflection that the little dot is going to have depends on the current that runs in the coil. The current controls the magnetic field, and the magnetic field controls the dot, so, you know, the current needs to be something specific. So the Vectrex, you know, very basically does it as such. You have a big ass amplifier that is put in there as an operational amplifier, and what it'll do is the schematic is such that the operational amplifier has feedback. And what that means is that if you put a certain voltage on one side, it'll try to regulate its output in such a way that the voltage on the other side is the same. It'll do something magic in order to make those two the same, more or less. So in this case, the negative input can only be half a volt when the current through the 1 ohm resistor is half an amp. That is Ohm's law. What that means is that the current through the coil is also half an amp. So I can say, okay, if I want to run a certain current through my coil, I need to put the same voltage on my input. This is great because it works fine, and you don't need to worry about like your coil not being ideal and stuff. There's a downside as well. Say that in order to get that half amp at a particular point in time, the amplifier needs to put 4.5 volt into the coil. Well, in the Vectrex at least, the power supply for the amplifier is 9 volts, which means that 4.5 volts will just get wasted away. It needs to burn that up, which makes the thing pretty hot. And you can actually see that is correct because the Vectrex contains a very big heatsink, which is just there for the deflection amplifier. So I can't really have that because, well, first of all, it's very power hungry, and ideally, if possible, I'd like to, you know, power these things from batteries and have more than like 3 seconds of battery life. It also needs the space for a heatsink, and this is a handheld device, so I'd like to keep it as small as possible. And also, you know, you have this in your hands. You don't want to burn your hands because the deflection is a little bit too much. So I need to figure out a different way to do that. And it took a few iterations, but in the end, what I did was make this. This is effectively an H-bridge made of MOSFETs. The actual implementation is a little bit different. I'll get into that later. And what it can do, like an H-bridge, is effectively connect the deflection coil to the power supply in different ways. So I can connect it like this, and in this case, one end of the deflection coil is connected to the power supply, and the other one is connected to ground. And if you remember the pig, that will make the current increase. I can connect it like this, like both sides to the ground, in which case I effectively short-circuit it, in which case, ideally, the current will stay the same. And finally, I can connect it the other way around, and that means that the voltage will effectively be negative, which means that the current will go down and will go negative if you wait long enough. Okay, that's great, but you know, the analog circuit had feedback, and we also put feedback in here. Well, you would need to put a shunt in here in order to convert the current to voltage, but then like neither side of your shunt is grounded, so you would need an instrumentation amp to you know, find the difference between the two pins of the resistor. And then you would need to put it in an ADC because everything is controlled from your FPGA, and your FPGA doesn't really have analog inputs. And that needs to be like, you know, a very big parallel bus because everything needs to be very fast. And unfortunately, fast bits are also pretty expensive. So, you know what? Maybe it's a better alternative to just not do any of that. Let's go with that. Okay, that's, you know, no components is the cheapest components. So, talking about components, as I said, the actual implementation of this are not MOSFETs. I found this great IC made by Texas Instruments. It's a half-bridge driver. It is tiny. It's ideal for this purpose, and it costs like $150-ish for one, and obviously less if you buy multiple of them. And they're tiny. They're so cute. This is a 5mm LED, 5mm LED as a comparison. And you might be, you know, this thing is tiny. Maybe it can drive like 1 amps or 2 amps or maybe 5 amps. Nope, 20 amps and 45 amps if you don't do it for that long. They're beasts, honestly. Anyway, with that aside, we still had the problem that we didn't have a way to measure the current. Well, I decided to just sidestep that by not measuring the current. So what I do instead is, you know, this is an inductor, and we know how an inductor works. There's math out there for that. So we can just simulate the entire thing in the FPGA. And then we can figure out what the current probably is. And actually, I don't do that one time. I do that 3 times for each of the 3 you know, configurations that I can have. And what I do is, if the circuit is in a certain state, and I want the inductance to go up or down to a certain level, I just simulate that for each of the 3 possible inputs I can give it. And I simply pick the one that gets the closest to the current that I want, and then I do that in real life. I update my model, and I do that over and over and over again. So that's great, it's a solution. It should look perfect, right? So I'm going to show you a bunch of images. On the left, there's the image from a simulator. On the right, there's the real image. And it looked... Oh. Okay, that's... it's kind of in there. So... you can see a few things here. First of all, the curves aren't entirely straight. The curves are curved, while they should be straight in the simulation. You can also see that there's a bit of keystone going on, etc. Those are all effects just from how the CRT physically works. I can compensate for that by doing distortion correction, and that's fine. The problem here are these things, because this means that the Vectrex is starting to draw a line and then returns to the starting point and draws the second half of the line. And in theory, it should start in both lines at the exact same point, but it doesn't. So at some point, it wanders. So why is that? Well, maybe you know, we're using the model of an ideal coil here, and you know, just to see if I'm wrong with that ideal coil, I tried to order one, but I think it's the component shortage or something. I couldn't. So rather than that, maybe we should dive into the model of a non-ideal coil. So this is what a non-ideal coil looks like, and this is still a little bit complicated. I really wouldn't like to implement this in an FPGA, but you know, maybe we can simplify it a little bit more. So these two, this inductance and this capacitance comes from the leads. You know, a coil needs to have leads to it, otherwise it doesn't do anything. And leads are conductors, and they are in parallel, so they will have some capacitance and inductance. And I'm just going to say that, you know, we'll just take our leads and make it very short compared to the actual coil winding. So we can just get rid of that. And then we have the capacitance of the coil. That is the capacitance between the windings. You have lots of windings, and they're all in parallel, so they will have a certain capacitance. And that capacitance is a little bit of a pain, because if you switch the power supply, you first need to have a bunch of current running through that capacitor in order to charge it up to the level of the power supply. And you know, it takes a certain amount of time depending on the current to do that. But you know, current, we had oodles of that, right? 45 amps. So this capacitor is going to be charged in absolutely no time at all. So we can happily ignore it. So that simplifies our complicated model a lot, because now you only have the actual ideal inductance as well as a model for the resistance of you know, the coil. I mean, it's made of pretty thin wire, so I unfortunately can't just, you know, get rid of that. So we have to model that, but that's just a resistance. We know how that works. And if we try that, it suddenly improves by a lot. This is what you get. So these are the same things. And as you can see, there's still distortion. There's a lot of keystoning going on, and what you can see right now is that there's also some barrel distortion and some other types of stuff. But that is all because of the physics of the screen, and given the fact that we can now address each point and know where the electron beam is, we can just compensate for that in the FPGA. So that's great. We have a working prototype. Well, I'm just going to jump ahead a lot and go to the hardware. And I'm not even going to show you the design process. I'm just going to show you the PCBs. So this is the first PCB I made, and this is a replacement for the PCB in the module. So this sits under the deflection coils and the electron beam. Just to outline it a little bit, there's a bit of power supply here. I need 6.5 volt, 10 volts, and 5 volts, and these are generated here, just a bunch of buck and boost converters. The flyback transformers here, plus all the potentiometers that you gotta tweak in order to get everything right. The G1 DAC is up top, and the op amps to do the rest are down there. We've got the little deflection coil drivers here. I told you they're tiny. Sorry, I can't get over that. There's a little audio amp in here. I just ignored it. It's just an audio amp. You want to hear the Vectrex, obviously. And finally, there are two connectors in order to connect an analog joystick to it. The Vectrex actually used an analog joystick, as well as a bunch of buttons. So there's a second PCB that mostly contains the FPGA board. So this is the top, just, you know, the FPGA board. And on the bottom, the most important part is here. There's a connector plus a bunch of level shifters, because obviously I want to put my original cartridges in here. And cartridges are 5 volts, FPGA is 3.3 volts. You need a bunch of level switches. But I don't have all the cartridges, unfortunately. I have exactly 2, and I do want to play the rest of the games as well. So there's a little micro SD slot here. And here are the connectors that connected to the rest of the board. So this is what it looks like assembled. As I said, the board is a replacement for the original board in the module. Joystick sits up top. And if you turn it around, it looks like this. The FPGA thing is a little backpack, and that also gives you space to insert the cartridge. Obviously, you do want to have a case, not only because it looks nice, but also because there's 400 volts there, so no touchy. So I decided to just design a case. This is open SCAT, so this is it closed, and this is it opened. It's a clamshell design. It hooks in with a bunch of tabs at the top, and it screws shut with a bunch of M3 screws at the bottom. I was lazy. I didn't want to design everything, so the buttons and the battery holder I just bought. So this is it partially assembled. The FPGA board goes in the bottom. Little connector for the battery power. The CRT module with the replacement PCB goes on top. And finally, you can close the case. Buttons are installed, there's a little speaker installed. And I actually made 2 prototypes, and they're both here, a red one and a black one. So, thanks. We're not entirely done yet, because I still need to talk a little bit about the FPGA load. As I said, we need to have the basics. So it's the Vectrex emulation core. It's connected to the buttons and the joystick via an ATC and just a bunch of GPIOs. I used a PWM generator within the FPGA to generate the audio. And here's the coil model I talked about earlier, plus the distortion correction for the keystoning, etc., to get a straight image. And initially I ran this off an external cartridge, but as I said, I kind of want to play games that I don't necessarily own the cartridge from, let's put it like that. So there's a switch there, and you can also connect it to a region in the SD-RAM in order to play from that. Well, obviously the SD-RAM is not gonna magically have Vectrex cartridges up here, so I need a bunch more, and I implemented that by using a separate CPU. So it's connected to the SD card interface here. There's a RISC-V CPU here that runs a little bare metal bit of code that interprets the FAT file system on the micro SD card and does other things. And there's a UART with a debug connector, which is very useful because I can just connect my laptop to it, and I can look at the screen, and I can tweak the coil model and the distortion correction parameters until they're just right, and then I can just save it into Flash EEPROM. So there's a little bit more in there because I want to be able to select which card to run off the SD card. And actually someone already made a multi-card for the oh wait, that was me. So this is a project I did like 8 years ago now. That is a multi-card based around an STM ARM4 chip. And I made that project open source, and other people came and ran with that and improved the firmware by a lot and made it into its own thing. And because it still was open source, you can just get the firmware back and get like a really fancy menu with features that I didn't even code. Open source is great. Oh, and also a screenshot of the console if you want to. So you can tweak the distortion parameters, etc. with this. You can calibrate the joystick because analog joystick. But you can also set breakpoints in the 6809 code, for instance, which is really useful if you introduce some sort of bug and your games don't run anymore. Okay, so on to the final result. I shot a little video. I can demonstrate it here, but screen is not that large, and I'm decently sure that if you're watching this on video, that this flickers like nothing else. Vector video games are a bit hard to shoot. So we'll just go and watch the video. So this is how it starts up. Takes a while because the CRT needs to warm up. Like later on, I cut this introduction sound, by the way. I tried to keep it a little bit short. So this is the built-in game. It's called Mindstorm. And I'm gonna utterly destroy this level, so I hope you don't mind the explosion sounds. So you might also be seeing that the lines are a little bit clotted. That is the intensity circuit that oscillates. That is the reason why it's not great. Last one. Yay! Okay, so let's turn it off, and let me put in an actual cartridge. It's great because this cartridge has a copyright of 1982. This is a 40-year-old cartridge in a machine that I just made. So this is Starship. It's I think in the USA it's called Star Trek, and you're shooting. Well, this is the European version, so you're shooting not Klingons here. And this cartridge was actually great because the star field moving around really looks off if your distortion correction is not correct. So again, the dotted lines, like my intensity circuit is not great. There's another one. Oh, you can evade the rockets by just moving them off screen, then they won't hit you. It's great. So multi-card takes a tiny micro SD card. It has to do so many other things nowadays. And this is the multi-card menu I told you about. It's got nice vectorized graphics. Just starting up a game. This is Berserk. This has been on lots and lots of consoles. I don't exactly know how it works aside from just shooting the guy and then turning it off because you're bored. The flickering is actually worse in real life. For some reason, this game really flickers. Yeah, shoot the guys or something, I don't know. So, one last thing I'd like to show you at least a bit of is that the Vectrex is also known in the demo scene. There have been 1 or 2 demos for it, which are pretty great. I don't know how we are on time, but I'd like to show you at least a little bit of that. This demo is called Where Have All the Pixels Gone? This flickering is on purpose. Also using those 3 channels of sound absolutely to the max. And like stuff like this, scaling was impossible on any game console around that time. Or at least pretty hard. Again, those lines are not supposed to be dotted, that's my mistake. Okay, that's the end. Thank you very much. I still have a last few things that I want to mention. First of all, this is all going to be open source as soon as I'm done, like not being tired from preparing the presentation anymore. Yeah, I told you about the intensity circuit. If someone knows a little bit more about like op amps and crap and can tell me what the hell I'm doing wrong, then by all means. I need to make more games work. Not that they don't work. If you have a cartridge, the thing should actually be more or less 100% compatible with any cartridge that's out there. But if you don't have a cartridge, some cartridges use interesting tricks, like they use flash memory that they write to, they use multi-banking schemes, etc. And the multi-card software that I have at the moment doesn't know what to do with that, so it doesn't start. It would be nice if those things could work as well. And finally, there's also a bunch of vector arcade machines, and in theory, this thing contains an FPGA, so you could reconfigure it to run those as well. So, you know, that might be an idea. A few things I'd like to thank. So first of all, Vectream, the menu software that I used is made by a bunch of people, some of whom are watching the stream. So thank you very much for improving my stuff. And finally, Claude Schwartz. 15 years ago, I was working on another project that involved an arcade monitor and reproducing an arcade video game. And I told him that, and he was like, hey, I have a VHDL version of a Vectrex. Do you want to play with that? And that is how this all got started, so 15 years in total. And finally, you all. I would never finish these projects if I wouldn't know that there are people who would be entertained by seeing this, looking at all this. This is effectively art. This is something that doesn't make sense to make. I am building something using a CRT that they stopped making before some of the chips that I use got started making. So this doesn't make sense. The only way it makes sense is because I want this to exist, and I know that you guys love hearing and reading about stuff like this existing. So thank you very much for that. Okay, final things. Thank you for listening. My name was Jeroen Domburg. My nick is SpriteTM, as you heard by the non-introduction. My website is spritesmods.com. I am on very fuzzy thingies as that. And I do have both the prototypes of the Vectrex with me. So if you want to give it a go, just find me and you can play a game as long as batteries last. Okay, thank you very much.